All right. Last time we defined conditional PDFs. Those are the probability density functions for continuous random variables conditioned on an event or conditioned on another random variable. This part will be similar to a review. The computing conditional expectation. The conditional expectation of a continuous random variable is defined similarly to expectation. The only difference is that we use conditional PDFs. So I suggest you fill in the integrals, these 4 integrals here. Let's do that together. The expected value of x given a is the integral of x times the conditional PDF f x given a is an event, x given a dx, right? This integral is done, computed from negative infinity to positive infinity. Similarly, the expected value of a function of the random variable x under the condition a is found by integrating g of x f x given a dx. What's next? Now we condition on another continuous random variable taking on the value y. Okay, the expected value of x given y equals y. Let's remember what this means. Y here is a continuous random variable. It will not take the particular value script y with non-zero probability, most likely. But still we can condition on this event. Given that y takes on the value small y, what is the expectation of x? All we need to do is use the conditional PDF fx given y dx, right? Similarly, the expected value of g of x given y equals y is integral from negative infinity to infinity x times g of x times fx given y dx. This should be clear because it's at this point it's more like a review than anything new. What's next? Let's do an example. Let's consider a random variable u, which is uniform in the interval from 0 to 100. Find the expectation of u given b, where b is the event that u is bigger than 60, compared to the expectation of u, unconditional expectation of u. So let's think about u. U has a PDF. Let's call it fu of x if you want, as a function of x, and it's constant in the interval from 0 to 100. The level should be 1 over 100, of course. What is the expectation of u? That's the center of gravity of the distribution, and it's trivially equal to 50. No problem. Now we are asked to find the expected value of u given the event b. The event b, what is the event b? B is the event that u is bigger than 60. So if we look over here, the expected value of x given a is x times the conditional density of x given a. That is exactly in this form. This is exactly in that form. So this is x times f u given b, x given b. If you want, actually, we don't have to keep writing b here. If you want, you can drop this b. It's up to you. After all, it's just a function of x here, and it's just a function of x here. What is x? X is the value that u takes, dx. Now, we need fu given b. We know how to compute fu given b. Let's do that. Fu given b of u. How do we do this? If you want, let's use x again. Well, that is simply fu of x normalized by the probability of the event B, provided x is in B and 0 otherwise. So for our example, this translates into simply fu given B of x is equal to 1 over 100 divided by the probability of B. What is the probability of B? The probability that u is in this range is given by the right 1 over 40. So 1 over 100 normalized by 1 over 40 whenever x is bigger than 60. And of course, bigger than 60 and less than 100, and 0 otherwise. Okay? So we need to compute this integral. Yes, please. Oh, 1 over 40 times 60. Wait. Let's see. Why did I write 1 over 40 here? This is 1 over 40. This is going to be 1 over 40. I'm sorry. Thank you for the correction. What is the probability of B? The probability of B is simply 40 times 1 over 100, which is, as you said, 2 over 5. Right. The probability of B is 2/5, which follows by inspecting this figure. Okay? Now, here we divide 1 over 100 by 2 over 5. And what do we get? We get that fu given B of x is equal to what? 5 over 1 over 40 if x is between 60 and 100 and 0 otherwise. So, as expected, it is uniform between 60 and 100. Let's plot this. fu given B of x is constant between 60 and 100, and its height is equal to 1 over 40. Why? Because the conditional PDF has to integrate to 1. Okay, so let's finish doing this integral. This integral is equal to the integral from 60 to 100, x times 1 over 40 dx, and it comes out to be 80. Right? Because it's the midpoint of the interval between 60 and 100. So this is the answer to our example. Any questions? Okay, now let's look again at the view graph. Let's remind ourselves the total expectation theorem. The total expectation theorem is a way of making the total probability theorem useful when computing expectations. So the expected value of x can be found when you have a partition of the sample space by taking a weighted sum of the conditional expectations. So expected value of x given A times the probability of A plus the expected value of x given A complement times the probability of A complement. Showing that this is true for continuous distributions follows simply, in similar ways to how we proved it in the discrete case. I leave the proof to you as exercise, but you can guess that it's quite intuitive. In general, if AIs are a disjoint partition of the sample space, then we can write the expected value of x as the summation expected value of x given AI times the probability of AI, where I go from 1 to n. All this is just like a review, so I'm not dwelling too much over them unless you have questions. Because we proved all of these and use all of these in the discrete case. Similarly, for completeness, let's write the expectation of g of x. The expectation of g of x can also be found using the total expectation theorem as the expectation of g of x given a times the probability of a plus the expectation of g of x given a complement times the probability of a complement. Let's use these in an exercise. Here's the example. A coin is tossed 5 times. Very nice. If we knew the probability of heads, then the number of heads in 5 tosses would be binomial. Now, knowing that the probability of heads is a random variable, p, uniformly distributed in 0.4 to 0.7, find the expected value of the number of heads to be observed. Now, the difference of this from the previous, from the usual case where the probability of heads is a deterministic number, is now the probability of heads is itself a random variable. So we need to condition on it taking a certain value and sort of take an expectation over the distribution of p. Let me go slowly with this example. I think this is very fundamental. This example is one of the canonical examples, I think, of this class, and it's important for you to be able to do a computation like this. So, basically there are 2 random variables nested in each other, one inside the other. The number of heads in 5 tosses. Let's call that, what shall we name it? What? H? Okay. What? All right. Let H be the number of, well, I don't think that H, anyway, heads in 5 tosses. Okay? Is H discrete or continuous? Of course, it's discrete. The only thing is we don't know its probability mass function. What else do we know? Given that p is equal to small p, so if they give us the probability of heads in any toss as small p, then I know the PMF of H. What is the PMF of H? The probability of H being equal to K given P equals small p is equal to what? Well, 5 choose K, P to the K, 1 minus P to the 5 minus K, as long as K is between 0 and 5, and 0 for other values of K. Okay, I know this. Yes, please. Okay. if they specify the probability of heads as P, then it's back to the usual 5 coin tosses, independent, equally likely, Bernoulli trials, and the number of successes in 5 Bernoulli trials with probability of success P in each trial is a binomial, okay, with parameters 5, n equals 5. Let's write this. This is a binomial distribution with n equals 5 and P equals P, the probability of success P. Okay? So, let me ask you a question. What is the expectation of H given P equals P? Given that the probability of getting heads in each toss is specified to be small, lowercase p. Very nice, 5 times p. Because the number of tosses is fixed at 5, n is 5. So it's 5 times p. Okay, but in general, when the probability of success is a random variable big P, then I can write this expectation of H given P in terms of the random variable capital P. So this expectation is random. It depends on the success probability or heads probability. Since it's a random variable, I can take its expectation. Right? I can take the expected value of H given P, which is the expected value of 5P. Right? What is the expected value of 5P? It is 5 times the expectation of P. Well, P is uniform from 0.4 to 0.7, so its expectation is 0.55. 0.4 plus 0.7 divided by 2. So this is 0.55. So this comes out to be 2.75. 2.75. Are there any questions? Now, we did this one way by writing the expected value of H in terms of the random variable P. Now, I would like to basically use the integration expression that we proved earlier, we wrote earlier today. So let's do an alternative solution for this. Essentially using the total expectation theorem. So the expected value of H is equal to integral expected value of H given P equals P times the density of P, okay, dP. What am I using here? I'm using the total expectation theorem. Well, we can take P from negative infinity to infinity because we haven't placed the actual function Fp of P yet. Is this expression clear? Let me know if you have a question about this. So, it is nothing but the total expectation theorem. The expected value of H can be found by taking a weighted sum. In this case, it's an integral. Expected value of H given P is this times the density of P. What I wrote here is an open form of this. Okay? So let's continue with this. This is the integral from minus infinity to infinity. The expected value of h given the probability of success being p. That's equal to 5 times p. 5p times fp of p dp. Let's now substitute fp of p in its place from 0.4 to 0.7. 5p times 1 over, what is the height of the density? 1 over 0.3. Huh? Yes. Or 10 over 3, yes. We just have this integral. And basically, this is equal to 5 times 0.55, which is 2.75. Any questions? I think you guys have a question. No? Yes, please. Okay. Now, P, that's Fp of P. Fp of P is uniform between 0.4 to 0.7. To make computations easy, we are using uniform PDFs. We could have had another PDF for Fp, but it's just uniform. And this range is 0.3, so this height should be 1 over 0.3, which is 10 over 3. Okay. Any other questions? What's next? Let's go to the next thing. The next topic is independence. Okay. Now we know conditional densities. Yes, please.
HP bizim normal durumdan expectation x NP'dir. Oradan gelen şey değil mi hocam?
Yes. Because we are multiplying by the density, this density, which is a function of p. It's a function of p. Okay, and we are integrating over p. So let me remind you this. Consider x and y. Okay, we want to compute the expectation of y. Okay, the expectation of y. Okay, everybody please listen. Okay, expectation of y is, I'll start from scratch. Y times fxy xy dx dy, double integral. Right? Any problem? Okay. And x goes from negative infinity to positive infinity, y goes from negative infinity to positive infinity. Now, here's what I'm going to do. I'm going to split this as f y given x times fx of x. Why can I do this? I can do this because the conditional density fy given x is defined. We defined this and motivated this. Of course, motivated the definition, explained the definition, but it's a definition after all. F xy divided by fx of x, right? So we we can write the joint density by multiplying fx and fy given x. Okay, I did this. So Now I'm going to simply sort of put the x integral outside. So I'll have dx on the outside, fx of x on the outside. And inside I'm going to have dy, y, f, y given x, y given x. Okay? So y goes from negative infinity to infinity, and x goes from negative infinity to infinity. All I did is I sort of put this integral together and, you know, got fx of x outside the integral. Now, can you tell me what the inner integral is? Expectation of y given x is equal to small x. Very nice. So let me rewrite this. This is integral from negative infinity to infinity, expected value of y given x is equal to x times fx of x dx. So we just showed that expected value of y can be found by finding the expected value of y given x equals x times fx of x integrated over all x. Now, this is exactly what we used here. Instead of x, we have h. Instead of y, we have p. Any problem? So let me repeat. This is the total expectation theorem. It's nothing but a short way of writing a double integral. Okay? No problem, I hope. So let's continue. The next topic is independence for continuous random variables. So in general, two random variables, discrete or continuous or in general, they are called independent if for any two events A and B, the probability that x is equal to x, x is in A and y is in B can be broken up into the product x is in A times the probability that y is in B. If you can do this for any arbitrary sets A and B, then the two random variables x and y are said to be independent. Now, in the case where x and y are continuous random variables, they have densities and they have a joint density. Okay? So, suppose x and y have the joint density fxy, xy. And that joint density breaks up into the product of marginals. Show that this condition implies the independence of x and y. Interesting. What are we asked to do? We are given that the joint density factors out into the product of the marginal densities, and we are asked to show that this implies independence. What is the definition of independence? The definition of independence is for any two sets A and B, the probability that x is in A while y is in B is equal to the product of the individual probabilities. So we need to be able to show that this is true for any sets A and B, provided this condition holds. Okay, so let's show that. fxy, xy is equal to fx of x times fy of y is what we have. So we are asked to compute the probability that x is in A and y is in B for any A and B, arbitrary subsets of real numbers A and B. So this joint probability can be found by integrating while x is in A and y is in B of the joint density. Okay. But by the assumption, this assumption, the joint density breaks down into this product. So the integral breaks into the product of two integrals. The integral factorizes. You see that, right? Because this is not a function of y, and this is not a function of x. So the joint integral breaks down into the product of two integrals. The outer integral, I mean, this first integral is over a, this integral is over b, but this is by definition the probability that x is in a, and this one is by definition the probability that y is in b. So we're done. So now we know that if the joint density fxy factorizes into the product of marginals, then x and y are independent. In fact, this condition is also necessary for independence. Here we showed sufficiency of the condition, but it's also necessary. So it's an if and only if statement. X and y, continuous random variables, are independent if and only if the joint factorizes into the product of marginals. Okay. Checking that the two random variables are independent requires checking that condition then, this condition. However, checking that they're not independent is sometimes easier, as you know from the discrete case. Sometimes just by looking at the region of the joint PMF or PDF, you can understand that they are not independent. Let's see this example. fxy is a constant whenever x is between 0 and 1 and y is between 0 and x. So let's see if they are dependent. Let's find the conditional densities, etc. So x is between 0 and 1. And y is between 0 and x. So this must be the region. It's a constant in this region. The value of c must be 1 over the area. What is the area? Area is 1/2, so c must be 2. Right? Okay. Are they independent, do you think? Are they independent? Why not? Well, first of all, if you give me the value of x, that determines the range of y, and that differs from x, one value of x to another. But to fully show it analytically, let's compute the marginals. Let's see. What is fx of x? This is sort of like an exercise of past topics. Fx of x is, well, fxy, xy, dy. Now, what is fxy? fxy is equal to c whenever, for any given value of x, suppose x is here, y goes from 0 to x. Okay? So 0 to x, c times dy. And that is cx, provided x is between 0 and 1 and 0 otherwise. Right? So that's fx of x. It looks like this. 2x. Let's write 2x. Oops. Okay, that's the marginal of x. Let's find the marginal of y, fy of y. What is the area of this triangle? 1/2. So the constant, well, but we want the PDF, the joint PDF, to integrate to 1 when we integrate over that region. And it's going to give us the volume of the region. The volume of the region should be 1, which means since the base is equal to 1/2, the height should be 2. Okay? It's a prism. It makes things easy. In general, I mean, of course, you can't go like this in general. If the height is not a constant here, then you have to really integrate and set the volume equal to 1. Okay, Fy of y is equal to, so given a value of y, x goes from something to 1. What is that something? X. No. Given a value of y, the range of x. I'm asking for the range of x. Y to 1, right? Okay. Given y is equal to y0, x goes from y0 to 1. X goes from y to 1. We have 2 dx. So the integral is equal to 2 times 1 minus y, as long as y is between 0 and 1 and 0 otherwise. So that is the marginal of y. Let's try to plot it, if you will. Fy of y, 0 to 1. Let me put my 1 over here. 2 times 1 minus y. 2 times 0 is here. Okay. So now let's compute fx of x times fy of y. That is 2x times 2 times 1 minus y whenever x and y are between 0 and 1, and x is bigger than y. This is the product of the marginals, and this is not equal to fxy of x and y. In fact, when we do this product, we don't have this additional condition, if you realize, because this first function is valid for any x between 0 and 1. The second function is valid for any y between 0 and 1. So the product is valid for any x and y between 0 and 1. Which is different from this clearly because it's just 2 in that range. And in fact, it's 0 in some part of this range. Do you see this? So fxy is different from fx times fy, which clearly proves that they are dependent random variables. But we already knew from the shape of the region, okay, that they were dependent. What's the time, please? How many minutes? Okay, any questions? Is this clear? Let's give a break at this point, and we'll start after the break.